Okay, so this theorem has an immediate corollary. Let X, together with some topology tau, be a topological space. A subset A of the space X is closed if and only if that set contains its derived set. So proof. Suppose that the set A is closed. Then the set A is equal to its closure, which was demonstrated is the union of the set with its derived set. And so the derived set is a subset of the set A, since it is a subset of any union which contains it. So conversely, suppose that the set A contains its derived set, then A prime union A is a subset of A union A, which is the set A. That is, the closure of the set A is a subset of the set A. Now, since in general any set is a subset of its closure, we now have set inclusion in both directions, and so the set A is equal to its closure, and hence the set A is closed. Okay, so next we will look at an example. Again, let X together with some topology tau be a topological space. And let the set A be a subset of the space X. Then the closure of A is once again the union of A with its derived set. And so we can think of the closure as an operation on the set which adds to the set all of its cluster points. And this is another reason why I prefer the functional notation for the closure. Now, the closure of A is also equal to the union of the set with its boundary. However, in general, the derived set is not equal to the boundary. These are two very different concepts around the set A. We're concerned with the set A. So we will show that in general, A prime is not equal to the boundary of A with a counterexample, and we'll take a counterexample in a Sierpinski space. So let the set X be the set containing the points A and B with the topology containing the empty set, the singleton set containing A, and the entire set. We will consider the subset A, which is the singleton set containing the point B. Notice that this is a closed set, since its complement is the singleton containing the point A, which is in the topology, that is, it is open. So the set A is its own closure. There is no open set which contains the singleton containing B, and so the interior of A is empty. And so the boundary of this set is its closure, set minus the interior, which is the set A. It is its own boundary. Now notice that the only open neighborhood of the point B is the entire set. Now, since the intersection of the entire set with the set A, again, which is the singleton containing B, is the singleton containing B, there does not exist an open neighborhood of the point B that intersects the set A in a point different from B. And so the point B is not a cluster point. Of the set A, and thus the point B is not in the derived set. Also notice that the singleton set containing A is an open neighborhood of the point A, such that the intersection of this neighborhood with the set A is empty. And so the point A is not in the closure of the set A, which again is the union of A with the derived set of A. And thus the point A is not in the derived set of A. These are the only 2 points in the space, and hence the derived set is the empty set. And very clearly, the derived set is not equal to the boundary. Okay, so new definition. Let X together with some topology tau be a topological space. And let the set A be a subset of the space X. A point in the set A is an isolated point of the set A if and only if there exists an open neighborhood U of the point X such that the intersection of that neighborhood with the set A is the singleton set containing the point X. So let's look at an example. Let X be a countable set. With the topology, the power set of X, that is the discrete topology on X, and let the set A be a subset of the space. Then every point in the set A is an isolated point of the set A. So proof. In the discrete topology, on the set X, every singleton set is open. And so for every point in the set A, the singleton set containing that point is an open neighborhood of the point such that the intersection of that neighborhood with the set A is the singleton containing that point. That is, every point in the set A is an isolated point. Of the set A. Now recall earlier that we demonstrated that for a given subset in a discrete space that that subset has no cluster points, and we have just demonstrated that every point in the set is an isolated point. And so for a given set, a point is either a cluster point or an isolated point of the set. So we will next prove this. So theorem. Again, let the set X together with some topology tau be a topological space. And let the set A be a subset of the space X. A point in the set, in the subset A, is either a cluster point of the set A or an isolated point of the set A, but not both. Now, notice that for a point to be an isolated point, it must be in the set. A cluster point need not be in the set, but for every point in the given set, that point is either a cluster point or an isolated point. So proof. Let X be a point in the set A, and suppose that this point is a cluster point. Of the set A. Then, for every open neighborhood of the point X, the intersection of that neighborhood with the complement of the singleton containing X in the set A is not empty. So there exists at least one point Y in the space X such that that point Y is in this intersection. Now, as the complement of the singleton containing X in A is a subset of the set A, we have that the union, or rather the intersection of U with this complement is a subset of the intersection of U with A. And so this point Y is in the intersection of the neighborhood U with A. This is true of all open neighborhoods of the point. And so there does not exist an open neighborhood of the point X such that the intersection of that neighborhood with the set A is the singleton containing X. And so this point X is not an isolated point. Of the set A. So now suppose that the set X, or rather the point X, is not a cluster point. Of the set A, then there exists at least one open neighborhood u of x such that the intersection of this neighborhood with the complement of the singleton containing x in A is empty. And so we can now take a union on both sides with the singleton containing the point x. So this, on the left-hand side, is the intersection of the union of the neighborhood of x with the singleton containing x, which is the neighborhood U, intersected with the union of the complement of the singleton with the singleton, which is the set A. And this is, on the right-hand side, the singleton containing x. And so that point x is an isolated point. Of the set A. Okay, so let's look at an example. Let tau sub I be the set which contains the empty set and the entire set of reals. Then this is the indiscrete or trivial topology on the reals. Consider the interval from A to B as a subset of the reals. Then, as this is a non-empty proper subset, it is neither open nor closed in this space. So notice that for every point in the entire space, the only open neighborhood of the point is, once again, the entire space. And so for every point in the entire space, the intersection of the only neighborhood of that point with the complement of the singleton containing that point in the interval from A to B is not empty. And so every point in the entire space is a cluster point of the interval from A to B. So every point in this interval is a cluster point, so this interval has no isolated points in this space. And so the derived set is the entire set of reals. The closure of this interval is once again the entire set of reals. So notice that the closure does indeed contain all of its cluster points. Now the boundary of this interval is the closure set minus the interior. The interior is empty, and so once again the boundary is the entire set of reals. And so in this case, the boundary of the interval is equal to the derived set of the interval. Okay, so as an exercise, let tau sub E be the union of the set which contains the reals with all subsets of the reals such that 0 is not in that subset. Then this is the excluded point topology on the reals with 0 the excluded point. Consider the interval from A to B inclusive of A and B, where A is strictly greater than 0. Then this is an open interval in this space. Determine the cluster points and isolated points of this interval. Alright, so we'll end here for today. Next time we will continue to look at the concept of isolated points. As we will see, this is a very important and descriptive, even characteristic property of a space, and we will also begin to look at some other important characteristic properties of spaces. So I hope you have enjoyed the fourth lecture. Thanks for watching.